So where are we? Hopefully I can put up the volume of the microphone a little more. Yeah, now should be better. To the max. Better. Better. Yeti. Is this using Yeti Nano? There we go. I think now I'm using the right microphone. So hopefully it's good. It doesn't look bad in OBS. And hopefully you can hear me better than in the previous videos. Apologies for that. I'll see if I can pull up the volume. Anyway, so a quick update, because I did a bit of a test on via Twitter stream, but I should probably do this here. I should probably do this here as well. What happened? Something got disconnected? No. Okay, it's all good. All seems to be good. Yes. So between there's a big gap between the last video and this video. So what I basically did, just for the record, I kind of had everything in one file. So I did multiple things. I basically, once I got it all working, right, in the last video, I split the whole thing into multiple files. I'm not so sure that's going to be the final split up. Doesn't matter. But I basically, carved aside sort of the neural network piece of it and added storing and loading functions. So it now basically, in a very naive way, just stores the matrices in here locally, and then you can load them as well. So so I can just basically do the training once and then play later with just examples. Then I kind of moved all the encoding functions in here, sort of the one that encodes a piece of input. So I kind of refactored a bit this as well. Before it was everything packed into sort of a loop, and then I had this function separately. Now I'm reusing this function all over the place, also for the training as well as for the testing element, not testing, but the actual is it really inference? I guess so, right? So the actual usage of the model. And then I have another file where I have the training stuff in there. So basically the training text, and then all the hyperparameters and all this kind of stuff. So, and in the main file, in the main script, I just have essentially, I instantiate the neural network, I load it, right? So I'm assuming I've trained it already. And then I basically do a prediction test, and then I have like an interactive prompt where I can just give in 5 words, and then it spits out something. So, and essentially, if I can do something like, but just basically, if I want to train something, I just say, look, I want to change some of these parameters. I want to do one epoch. I want to change the learning rate, and none of these works well, I'm sure. But at least sort of it works as like the pieces work together from an integration perspective. So I can just say Python train, and we'll actually do a training run. As I said, and the thing is, obviously that's not working well, but it will do the training run, and then I think it will output a. Take a look at the output later. It will output a It will output a visualization of a loss, which is obviously not working well. So now at least I have all these things separate, and I can just work on them, right? Because again, the goal of this project is to just play with these transformers thing, which the more that I work with these, the more I realize, to be honest, I'm not so sure what's that special about, like what's so special about it other than the encoding element of it. Of course, there's a lot of flavors, right? To do this like in a more general aspect, I would probably have longer inputs, longer outputs, not just like one word, right? And then, but I think I wanted to do a toy example once without any libraries, and I think then what I can do later is I can just pick something like PyTorch or pick something like TensorFlow and just see how I can do it there, right? But I wanted to first get these things right, so I'm still going to spend some time in here. You can see this is how the loss is evolving, which is just it's just crap, right? So there are now 2 things that I can work on, right? So this is just whatever. Now there are 2 things I can work on, 2 different paths that still need work. One is the actual attention mechanism, the actual, not attention, but like, well, attention is one thing, right? So it's 2 things. Obviously, this attention mechanism is just bullshit because it's just using random things. random matrices, and this is not being trained at all. The actual encoding is it's a very basic encoding, which while refactoring I realized it was wrong at all, because it was not actually even using the input. But one thing that I want to do is I just want to basically replace all these with encodings, not encodings, embeddings, right? See if I can just use embeddings. So, Ghost Rider, where are you, Ghost Rider? There you are, Ghost Rider. I don't know if Ghost Rider can suggest me that, but like, can you suggest some good embeddings? Are they libraries? Are these libraries? Like, how is this integrated? Popular for word embeddings, globe. So, is that an actual thing? Word representation. Okay. Because I guess that essentially just comes in with pre-trained word vectors. Yeah. So that essentially comes in with a vocabulary, and it comes in with the actual encoding. So I will just replace that with these. But then the attention aspect of it, that will be the next thing, right? So how to really train that? So when it comes to the attention mechanism, because what is the attention doing? So the attention was doing basically it was just looking at similarities, but it's not, it was not really training anything at all. Like, how do I comes to attention mechanism, how do I train? So what's the best practice, or the best way to train the WQ, WK, WV, WO, DO matrices. Because are there, like, because that is also based on your data, right? That is also based on your that's something you train on your training set, because that's what you want to do, right? So out there, that implement it, like, I guess so, right? So I'm assuming if I look for PyTorch multi-head attention, right? So PyTorch attention. I guess the next thing will just be getting to PyTorch, for example, right? So here you just have these basically implementations, autograd, blah 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 blah. How to use that multi-head attention example. So how do you use that in the context? How do you, so PyTorch multi-head attention, give me a code example, because I think I understand multi-head attention, multi-head attention, whatever, define input tensors, but how do you train it? You know what I mean? Like, do you need to train? So essentially in a transformers models, you need to train the attention mechanism, as well as, do you need to train the attention mechanism? Yes, because what it's doing is it's doing a dot product of like the query and the key. like that is the thing, right? So do you, like, I'm not so sure if you need that. Does the attention mechanism need to be trained? Because what's bothering me is that, so we've got basically, there's this piece here which is doing a dot product of the query with these random stuff, which, like, I'm not so sure it's really needed. Why is that even needed? You know what I mean? Like, cannot you just do attention of the query key and value and that's it? Because essentially you're doing similarities between the query and the key, and that is basically the way this is done in the training mechanism when they do the attention. No, it's in encoding when you do attention. The input is the query, is the word in the query, and then you do that directly on the word embedding. So you're just doing similarity. Like I think that makes no sense. I don't think that makes sense at all. He says no, the attention mechanism hasn't be trained separately. It is a component with a larger it's a component within a larger neural network model, and is typically trained alongside other model parameters. During the training process, the attention mechanism learns to assign different weights to different parts of the input sequences based on their relevance to the task at hand. It is typically initialized randomly. I mean, it is with pre-trained weights. It is. Its parameters are updated during the backpropagation. So maybe, okay, really. Really? So you do need that, maybe. I mean, you do need that, because I think the reason for doing that is that you're basically actually doing a projection, and then the idea is these would find an optimal projection where you can kind of, you know. Okay, so to-dos. Essentially, replace the positional encoding by just using embeddings. So we just have embeddings from a library, whatever. And then another thing is basically fix the neural network stuff. And so this is the multiple things, right? So on one hand is understand what the hell is going on here. On the second hand, I think that's why I wanted to focus, why I wanted to start diving into this today, is the backward propagation element here. So there are two things that need to happen here. One thing is the, like, is this at all correct? It doesn't seem to be. This in conjunction with the loss function, and where's the loss function? It's here. This loss function kind of seems to make no sense. So there are two things. So take a look at the loss function. Another thing is to take a look at the actual backward propagation method, and including here also these stuff, right? But of course for these I need a how do I do that, right? I need to calculate a loss over these, and then based on that, you know what I mean, like how to add here the attention mechanism. How to add here the attention mechanism? That's what makes it special, I guess. So how to add here the attention mechanism? Can this be done? Because backwards to backwards, x, y. I need to be able to calculate. Well, it is. There's some differential calculated rate. These stuff here. It's something like the output minus the expected output. I think that is kind of the. This is where we should put a lot of attention in the coming videos, right? That's where I don't really understand if that works well. But then, okay, so what is the difference and how to tweak it so that then the loss function kind of goes down. I guess our goal is to look at that output thing, which is probably lost now, and see that, oh, it's still there. Okay, so look at these and at least see a curve that kind of goes slowly down, right? So we want to see a loss that goes from top, like up, from like a high loss, the other way, minimize the loss, yeah. So it goes from high, it goes to less, right? So that's what we want to do. And I believe that regardless, I think we can leave the, I believe we can leave the attention mechanism out for now. That is just doing something. But if we focus on these, if we focus on two things, on the a better choice of a loss function, and then basically like, okay, is that, you know, is this gradient really well implemented? Is this actually, but I had the feeling there's something missing in here, because shouldn't the loss somehow be related to these? You know what I mean? Where do optimizers come? Like, isn't there a piece that's like of an algorithm that's like an optimizer? So, what's the role of an optimizer in a neural network? Oh no, okay, okay. So it seems they've removed the general. It's like the default mode. The roles and classes do not always mean as a loss function. Determines how the most parameters should be updated. That's kind of the thing. So there's no optimizer. Finding the optimal values of the most parameters that minimize the difference exactly. Stochastic gradient descent. I guess that's just stochastic gradient descent. I guess that's what it's doing, right? So I guess that's what it's just doing. Is basically shuffle training samples, iterate through the shuffle samples, compute a gradient of the loss function. That's the thing, right? So the gradient of the loss function with respect to the models parameters. That's what I'm missing. I'm missing that. I'm not so sure if that is the right thing to do with respect to this loss function. You know what I mean? And I think the loss function should be, I don't know whether this should be here or should be here somehow. Because that's very naive, right? It's just the difference between the logits, which is basically basically the output, right? And actually, it just makes no sense at all, because this makes no sense at all if you think about it. We apply the forward passes. No, it does. Okay, so the training loop does forward pass, then loss function, and then basically the backward pass. So that makes sense. It's like first as a forward pass, it calculates this logic, it's the output. Then the loss function is executed, and then the backward pass. So these p's here should be related to the loss function. So that's where we should get into, I guess, right now. Okay, let's get into these then. That's the first thing that I want to do, right? Loss functions. So can you give me, so, and then obviously we just can do this. We can just stick to these, right? Gradient descent. SGT Atom. This is an algorithm dating the parameters. So maybe. Okay, so can you give me a summary of optimization algorithms, loss functions, options, and best practices for transformer models. So we've got the ADAM, Adaptive Moment Estimation, is a popular optimization algorithm that combines benefits of both ADA-grad and RMS prop. It adapts the learning rate for each parameter based on the estimates of both first and second moments of the gradients. It also includes bias correction and momentum terms. ADAM-W is a variant of ADAM that introduces weight decay during the parameter. These are crazy stuff that helps prevent the model from overfitting and the training data, adding a localization term to the loss function. Okay. I think I should just go with something very basic first, because those guys, like, they probably require like sort of a, you know, a series of study sessions by themselves. It's a basic optimization that updates the model's parameters based on the gradients of the loss function with respect to randomly selected subset of training samples at each iteration. Okay. So we should probably implement these. Loss functions, cross entropy loss. Cross entropy loss is commonly used in classification tasks. For general models, it is typically used when the task involves predicting the probability distribution over the set of classes, such as language modeling or machine translation. I think that's what we could probably use for transformer models. Realization, attention, masking, model size, capacity, whatever. Mean square error, loss. Task of the model predicts continuous values. We're not. It's not a continuous value here. We're really doing classes, right? Because we're doing basically over each word in the vocabulary. So we're doing that. So I guess. That's what we. That's what we wanna do. Cross entropy. Okay, so we want to do cross entropy loss, and we want to do SGD. Okay, so how should I SGD and cross entropy loss for the current current project? So let's see, what is it doing here? Is that cross entropy law? Create an instance of your known class, define the learning rate and the number of epochs for training. Iterate through the training data for the specific number of epochs. Within each epoch, iterate through the training samples. For each sample, compute the forward pass. Or compute the gradients using backpropagation method in another class. That's a very I don't like that answer. It seems to just have gotten my current code base and just kind of explained it back to me. You know what I mean? Cross entropy loss. So give me the code for cross entropy loss. Is it like that? Cross entropy loss Python. Yeah, is it really cross entropy machine learning? Cross entropy loss. My God, the pop-ups. It's a negative sum of okay. It doesn't seem to be like exactly like that. So explain me how to how to implement and what I have these probability distributions, I guess. The true labels. The predicted probabilities. Inside the loss function, it calculates the negative logarithm of the predict. I don't want to explain code. I want default. Let's just do default. The problem is that it tends to just explain the code, and that's what I don't. So cross entropy loss is a commonly used loss function in classification tasks to measure the dissimilarity between predicted probabilities and the true labels. It quantifies how well the predicted probabilities match the true distribution of the classes. Softmax and predicted probabilities. Before computing cross entropy loss, it is common to apply the softmax function to the output of your model's final layer. The softmax function converts the logits, raw values, into a probability distribution over the classes. Okay. Is this doing that? So is forward doing softmax? Yes. So that's probabilities. Okay. True labels. Cross entropy requires the true labels for each sample in your training data. The true labels represent the actual class or category to which each sample belongs. So this is basically, typically true labels are represented as one-hot vectors where the index corresponds to true class is 1 and all. Okay, so that is done. So this is, I think this is correct. That's this basically. No, that is the y loss function. Y. Not correct though. Oh yeah. Select training. No. Output preferences. Is this output preferences? Okay, I'm not so sure that is correct though. Yeah, that is wrong. So this is definitely wrong in here. So that should actually be, you know what? That should actually be, this is what is given to, so what is given to basically, this. So y dist, exactly. So that's kind of, this stuff should be calculated. So there's the forward pass, there's the loss function. So this is the, you know, this is the expected distribution. So this should be given to the loss function instead of, so as this y true, exactly. Yeah. But then that's just wrong, right? This is just wrong. Calculation of cross entropy loss given the predicted probabilities, right? And the true labels, true for a sample, the calculation of cross entropy loss involves the following steps. To retrieve the predicted probabilities corresponding to the true label, y pred. Retrieve the predicted probabilities corresponding to the true label from y pred. So essentially get the highest. The output. So what is output t? That's the distribution predicted. Yeah. So this is a mess. The true label index. use the retrieved predicted probability in the formula to calculate the cross entropy loss. This formula calculates the negative logarithm of the predicted probability of the true class. The negative logarithm of the predicted probability penalizes the model more when it assigns low probabilities to the true class, as it suggests a higher deviation from the desired distribution. So essentially, negative logarithm. So can you plot? So negative logarithm. Give me negative logarithm. Can ghostwriter give me? No, probably can't. Plot. Zero and one. Although I don't think it can do this. It will give me code to do that. I can copy that, create a new file, test Python, do these, and then basically run. So open a shell or just kill this one and do Python test py and open the output. So yeah, the lower, okay, so the lower, I mean, yeah, it's kind of what you want, right? The lower the the higher the lower the probability, the higher negative, the higher the number, but then it's negative. So should I be? That's all I know. Should I be? It measures the average difference between the predicted probabilities and the true labels. It quantifies how well the models. Well, essentially, if it's 1, the log is 0, right? So then it's good. If it's 0 probability, it gives it. So what is minus log of 0? What is log of 0? Yeah, well, log. What is this log on what base? Is this base 10? I think it's base 10, isn't it? Or it's just a natural log. Can I trust it to calculate this? Can I trust it to calculate this? Probably not. Explain code. No. Don't fly away. Oh. Default. It's negative. Yeah, but then with the negative, so you want high because you want a high loss. Makes sense. Okay. So this means yeah, you want a high loss. High loss when it's low values, low loss when it's high, or like when it's close to 1. That makes sense. Okay. So yeah, whatever. That actually makes sense. Now the only thing is how do I so this kind of makes sense. It's just not done the right way. So let me just do this properly. So first of all, and then probably we'll just leave it here. So we have the y distribution That's the y-dist is basically the true distribution, which is take output size and then you know what y is. The output t is exactly, so what we need to do here is the y predicted. So we need to get index of highest value in ypred. Yeah, so ypred, and then basically take the highest index. That's the prediction. No, in y true. So as a true label, and then use the true index. Use the true index here. So, and you take a look at the ypred, take a look at the index, and then, yeah, and then that's the value, right? So then you do that. Can we try, see if that change just works well at all? Can I just do Python training pi? What's gonna break? I changed some stuff, so I'm not so sure if it's gonna break or not. Yeah, it's breaking. Where does it break? Loss function. Can I just get rid of this? Okay, it seems to be training, but now let's see if it's going down at all, but it doesn't look like. Because whatever, but it works, right? So the challenge now is to adapt that part here, right? Because this is what seems to be wrong. So in the back, what we're doing here in the backward pass, we're passing it the x1, we're passing the y distribution, which is the ideal value, and that's not what we should be passing it, I guess. That just makes no sense. If I look at the output, it just makes no sense. Exactly. So that's the next to do is to change that. I think that is where. So this is where SGD needs to be now implemented properly, right? So I guess I need to pass it the y-dist and the ypred, I guess. Do I need to give it the predicted? I don't know. This is sort of the next proper HDD here. I don't know if that's already what it's just, you know. Yeah, that's it. Anyway, see you in the next video, but that's where we need to, because at least I want to see the loss function going down, right? So even if it's not going down perfectly, because SGD might not be the most ideal optimizer for this or the algorithm for this, but at least I want to get that correct. See you next time.